Hello and welcome to my first video on registers. In this one we're going to be talking about a serial adder. And basically what it does is it adds two 4-bit numbers together, and it just does it in a little bit of a different way than what we're used to with full adders and that kind of thing. So we can go ahead and get started with the first part, which is we have this table here, and this isn't a truth table. This is kind of just it shows what happens in the circuit. So we look at the action tab, and this is kind of what we're doing or what the circuit's doing, and then it shows the states of the registers and then the D flip-flop as we continue down this chain. And the D flip-flop is basically just the carry out bit. So we can start by, we first clear the registers. So in case there was anything previously happening with the adder, we just make sure everything is at 0 so we can get a fresh start. And so the way that a serial adder works in this case is that we have to slowly load the bits onto the registers one at a time, because that's kind of what a serial adder is. It adds one bit from right to left, one at a time. So we first have to put bits onto register B, and then what that does is that once you put the bits onto register B, you actually load the bits from register B onto register A, and then add the new bits to register B at the same time. So for example, if we wanted to add 3 and 7, then we would first load 3 onto register B, and then we would take the bits from B and put them onto A, and then put 7 onto B. So we would put 3 onto B, and then 3 onto A from B, and then 7 onto B at the same time. And that's what this sort of transfer augend load addend step is. So the augend is going to go onto register A, and the addend is going onto register B. But again, we can't load them at the same time, so we have to do the augend first and then the addend. So that's kind of what the steps here are about. So when we're loading the augend, it's not like we're doing any computation or anything. We're literally just we have like a value, it's called the serial in number, and every clock cycle it adds whatever the value of the serial in number is to register B. So it'll take 4 clock cycles, as it says here, 4 pulses, and we'll start with 1 and we'll go 0, 0, 1, and that'll load onto register B. Now we have to transfer that augend and load the addend. And this is actually done by addition. When we transfer that augend. So it's not like the register B goes straight to register A. It's actually just register A is actually 0, 0, 0, 0, and register A is recording the sum of register A and register B, and then loading it onto register A. So, and this will all make a lot more sense when we look at the circuit, but just kind of take my word for it for now. So let's start the addition process, or the transfer the augend process. So if we look here, we're adding the least significant bits together as well as the carry out bit, or the carry in bit, I guess you could say. So it's 0 plus 1 plus 0. That records it in that order. And that ends up being 0, 1. 0 is the carry out bit, and 1 is the sum. So we see 0 is the carryout bit, and then 1 gets added to the most significant bit of register A. Everything here gets shifted over 1, and then whatever our desired value, the least significant bit of our next desired value is added to the most significant bit of register B. In that way, we can still perform the necessary computation to do the next step while also recording the least significant bit of the next value that we want to store in register B. And so we just keep doing this process. So we look at the least significant bit of A, add it to the least significant bit of B, add the carry in. 0 plus 0 plus 0 is 0, 0. 0 carry out, and 0 sum. So we add the sum to the most significant, or we sort of tack on the sum to the most significant bit of register A. We shift everything over by 1, and then we add we shift everything over by 1 for B, and then add in the next least significant bit from the next desirable stored value for register B. And this process continues until we get our desired value here, which is 11. And then also, this is now A. So what we originally had in register B is now stored in A, because again we just added 0 to this basically, and then now we have our second value. So now we can actually do the addition, and so that addition, it's the exact same thing as what we just did now, except now we're not actually trying to register a specific number into B, or we're not trying to store a specific number into B. And so that's why these X's come up here, because we're just adding the sum into A one bit at a time. We're recording the carryout bit, and we're doing the addition normally. However, so we're not storing a particular value. So every single clock pulse, we don't care about what is then stored into the most significant bits of register B because, well, we don't care. All we care about is the sum. And so that's kind of how this table is completed. And this will all make a lot more sense when we actually look at the circuit. So we can show how the circuit works. So we have this clear switch. That's what we're going to start out with. So we had numbers in here. So we clear everything first. Now everything is at 0. We have this enabler here that just says, like, are we going to allow this circuit to work or not? Basic enabler. And so we can start the process. So first we're going to load, this is register B and this is register A. First we're going to load our initial value onto B. So say we're going to do 3 plus 5. And that's going to give us 8. Theoretically, if the circuit works, let's go ahead and test it. So if we want 3, we're going to load in the least significant bits first. So we're going to load on a 1, and then another 1, and then we're going to load on 2 zeros. So that's 3. And now we're going to compute 3 plus 0, basically. And that's going to take 4 clock pulses. But at the same time, we're also going to load on our next number to B, which is 5. So that's going to be 4 plus 1 in this case. So we're going to want 1, 0, 1, 0. So we have a 1, 0, 1, 0. So now we have 5. So we have 5 here, and then, as you can see, 3 got loaded onto here. And now we can do the addition. And we don't actually care what B is. So we can just go for 3 more clock pulses. 1, 2, 3, 4. And now we have 8 stored in A. And our carryout bit, which is given by this, I should probably label that. Is given by this output here. You see we have 1, 0, 0, 0. We don't care about what's in here. And 1, 0, 0, 0 is 8, which is exactly what we predicted, showing that the circuit is actually functional. And so that is the completed circuit. Let's see here. Oh, I guess we could also show, we're supposed to show like the desired addition. So in the table we had 1, 0, 0, 1 plus 1, 0, 1, 1. So we can go ahead and do that now. So we'll go ahead and clear because we just did a computation. And so we want 1, 0, 1, 1. 1, 0, 0, 1 first. So we'll go 1, 0, 0, 1. And then we want 1, 0, 1, 1. So we want, let's see, 1, 0, 1, 1. So we have 2 1s, 1, 1, 0, 1. So 1001 plus 1011, and then we can compute the sum. So 1, 2, 3, 4, and the sum, which is supposed to be 10100, is exactly that. So we have a carryout bit, so that'll go in our 5th bit slot. So 10100. So working as it should. And finally, I'm given this question. Discuss the advantages and drawbacks of a serial adder sequential circuit as compared with a parallel adder combinational circuit. So a parallel adder combinational circuit, it requires 4 full adders. It is a combinational circuit, so it doesn't use any memory storing circuits. So in that case, we don't need to wait for a clock pulse. We don't have to account for any of the drawbacks that are associated with sequential circuits, like any errors that could happen as a result of clock pulses happening at unopportune times that could lead to it could lead to errors or anything like that. However, the disadvantage of a parallel adder is that it only uses 1 full adder. So we can compute, we can add 4 bits with a singular adder because we're able to store those carryout bits in memory with a D flip-flop. We do have to wait for the clock cycles to occur, but if they're happening at extremely rapid times, there's not really going to be very much delay. So it just kind of depends on what you want to do. The parallel adder will add everything basically instantly, whereas a serial adder has to do 1 bit at a time. So it depends on what you want to do, but they do have their their drawbacks and benefits. Especially just because they're 2 different kinds of circuits, sequential and combinational, and so just using those types of circuits in themselves have sort of inherent advantages and disadvantages. So yeah, that's all for this video. Thank you for watching, and we'll see you in the next video on registers. Thank you.